Hello, Dr. J here. We're going to do a continuous time inverse Fourier transform of a low-pass filter. As a way of review, let me give you the definition of both the Fourier transform and the inverse Fourier transform. We'll start off with the continuous time Fourier transform, which we're given this mathematically, where x j omega is equal to x sub t times e to the j omega t, integrating with respect to time going from minus infinity to infinity. The continuous time inverse Fourier transform is given as 1 over 2 pi multiplied by the integration going from minus infinity to infinity, where the integrand is x j omega e to the j positive j omega t d omega. This formula here for the Fourier transform is known as the analysis equation because we can extract frequency information. And the inverse Fourier transform is a synthesis equation because we can build signals from frequency information. So here we have the time domain for the Fourier time domain description of xt, and we want to convert that to the frequency domain and vice versa, where we given x of j omega and then find the time domain description. That's what our focus on is today for a low-pass filter. So now we're going to perform an inverse Fourier transform of an ideal low-pass filter. Here's our frequency domain description of our low-pass filter. It's a rectangular function having a width of 2w. We're going to apply the definition of this inverse Fourier transform. And here's our graphical depiction of our ideal low-pass filter. Has a width of 2w and a height of 1. Therefore, this has a cutoff frequency of w, and using symmetry, it has minus w in order to make this low-pass filter a real function. We're going to show that the Fourier inverse Fourier transform of this low-pass filter follows the form of a sinc as we define here. Sine of pi x divided by pi x. And so substituting our rect function, since it has a height of 1, we just put a 1 in our definition here. And we're integrating not from minus infinity to infinity, but from minus w to w. When we do that, we have the integral of an exponential is the same exponential with a scale factor of 1 over jt, because t is a constant with respect to this integral. Our upper limit is capital W and our lower limit is minus w. And we still have the scale factor of 1 over 2 pi. When we finish this integration, substituting the upper and lower limit, we have the form of e to the j wt minus e to the minus j wt. And if you notice this form, we can take this two complex exponentials, take the 2 and the j, and form a sign, because the definition of our sign with an argument of wt is e to the j wt minus e to the minus j wt divided by 2j. That's our definition of a sine function. When we apply this definition of the sine function, we're given x sub t equals 1 over pi t multiplied by the sine of wt. Now we want to take this and manipulate this function algebraically so we can get the form of a sine pi x divided by pi x. So what we're going to do is multiply this, or change the argument of the sine, where we add a w over pi and multiply by pi, so we don't change the function or change the argument inside the sine function. And then we want to have the same argument of the sine as in this denominator here, pi multiplied by w divided by pi times t. So we have to, so we don't change the overall function of this, we have to multiply this by pi, w over pi and w over pi, and see, so we can get the same function as shown here. So now we see that this definition, because there's a pi here and a pi here, and now we're highlighted this in red, we have that argument x. So x is basically wt divided by pi. And therefore, we finally have our definition of our sinc function scaled by w over pi times sinc with the argument of w over pi times t. So that's how you do the inverse Fourier transform of an ideal low-pass filter. So the inverse Fourier transform for our ideal low-pass filter is a sinc function scaled by W over pi. Notice that we have this reciprocal spreading again. What's wide in one domain gets thin in the other domain because of the reciprocal relationship between the bandwidth and the pulse width. And we define the pulse width for the sinc function in the time domain as the first zero, pi over W. So as W gets wider, this point right here approaches the origin. Also notice what's finite in one domain is infinite in the other domain. Notice the sinc function goes on to plus or minus infinity. So in other words, this ideal low-pass filter is not realizable because you have negative time, or that it's a non-causal system. Signing off is Dr. J. See you next time.